Suppose we have a system of linear equations, two equations at once, and we want to find a value for x and a value for y that will satisfy both equations at once. We already know how to solve it by graphing. We graph each of the two equations separately on the same axes, and the point where the two lines cross is our answer. We saw a whole module on that method, and in another module we saw how to solve it by substitution. We solved for one variable in terms of another. That gave us our key formula, which we then used as a tool to find the complete answer. If you're uncertain about any of that, take a look at those modules. In this one, we're going to see yet another way of doing the same thing. Why? Because you don't want to work any harder than you have to. In any particular case, you want to use the method that works best for you. On larger examples, for instance, this method, elimination, is going to work better than the others, especially if there are fractions. Great, but how does it work? That takes a little review. Remember when you started with linear equations, you saw a master plan that worked like this? That was when you discovered 4 different things you could do to an equation without changing the answers at all. That was for one equation. If we apply the same thing to a system of 2 equations, we find that multiplying and dividing work exactly as they did before. But adding and subtracting are something else. Add or subtract 2 equations. Can we do that? Will it work? Let's find out with 2 equations where we already know the answers. X equals 1 and y equals 2. We add the 2 equations together. X plus 2x is 3x. Y plus y is 2y. 3 plus 4 is 7, which gives us an entirely new equation, 3x plus 2y equals 7. Is it right? Did we combine the equations without changing our original answers? We substitute and find, yes, adding 2 equations works. What about subtracting? Take a look for yourself. Subtract the second equation from the first and see what you get. Very interesting. I suddenly find that y has disappeared and I have the correct solution for x. I have solved both equations by eliminating one variable, and that's how the elimination method works. What we want to do in this method is to combine the equations in such a way that one of our letters disappears, then find the value of the other one. That's easy. Let's see if we can handle a harder problem with the same basic approach. We want to make the x disappear, but in this case, simply adding or subtracting won't do it. What we have to do is to make the x coefficients the same. We can do that by multiplying. Since the lowest common denominator is 6, we have to multiply the entire first equation by 3 and the whole second equation by 2, or even better, by -2. Why -2? Because our 2 equations now begin with positive 6x and negative 6x. Add the equations together and the x terms disappear, just what we wanted. And now we can easily find the value of y, but we still don't have a value for x. More to do, and a choice of two ways to do it. We know we can find x by substitution, but just to stay in practice, let's do it by elimination first. This time we'll eliminate y to find x. The lowest common denominator of 3 and 5 is 15. To make both of the y coefficients equal 15, we multiply the whole first equation by 5, and we multiply the whole second equation by 3. This time we already have one positive and the other negative. So we add the two equations, y disappears entirely, and we have the answer for x. Remember that odd-looking fraction now, and we'll go back and do the same thing by substitution. Our value for y was 4/19. We substitute that value into the first of the two equations. We could use either one, of course, and solve for x. To get rid of the fraction, we multiply both sides of the equation by 19, simplify, and end up with x equals 51 over 19, the same answer we got by elimination. Finding the second variable by substitution or by elimination is a matter of choice. Do it the way you like best, because the answer has to be the same either way. But whenever you use the elimination method, keep the steps clearly in mind. Use the method now on this problem, and don't forget to find the second variable. As soon as you have both answers, turn the tape on. I can eliminate x first or y first, whichever I choose. I choose x. That means I want to make the coefficient of x 10 in both equations. So I multiply the first equation by 5. I multiply the second one by a -2 in order to produce negative 10x and positive 10x, which disappear when I add them together, leaving me the answer for y. Then I turn around and do the same thing for x. I want both coefficients for y to be 3. The first one already is, so I leave that equation alone. The second equation I multiply by -3 to give me a +3 and a -3, which disappear when I add them together, leaving me with x equals 25 over 13. You may recall that this is the same system of equations we solved in the module on substitution. And yes, we did get the same answers both times. And graphing also would give us the same answer, but it doesn't work very well with fractions. They're too hard to read on a graph. Still, it's a good idea to do the same problem by different methods to find out what works better on each kind of problem. You'll find more problems to work on in your textbook, of course. And if you're looking for more explanation, you'll find that too. Look at some more examples right away if you still have any questions about how this method works. The elimination method also works on word problems, provided that you translate them correctly from English into algebra. Here's one we also use in the module on substitution. Try doing it now by elimination. Just turn it into two equations and proceed from there. And just to be sure that you can check your answers, these are the ones we came up with in the other module. Good luck.